I would like to consider a problem that origins from the last century. We can remember the eternal monograph by Hardy. So here I represent a copy from the book. It's not my writing. It's a definition of a divergent series, but at the same time convergent in the Lidskii sense. You see, it's a copy of the extract from monograph Hardy. But for our issue, we should make proper mathematical definitions written in a proper way. So consider a linear operator L acting in a separable Hilbert space. The set, it's represented here, is called the numerical range of the operator L. The values of the form of operator, in other words. Define a sector in the complex plane in the following way. We use this denotation for a sector. The vertex of the sector situated at the point 0, and theta is half angle of the sector. A root vector of the operator L is defined by the formula. So here n is called by height, and this is some kind of platitude, but I think here we should recall notations. In accordance with the Hilbert theorem, an arbitrary non-zero spectral value of the compact operator L is a normal with the eigenvalue. It means the following: the dimension of the root vector subspace is finite, and the following decomposition holds. It's a decomposition of the Hilbert space in a direct sum. The root subspace corresponding to the eigenvalue lambda L, and parallel complement, not orthogonal, parallel complement, if we have a direct sum. So the property is the following: the operator B minus lambda identical operator is invertible on n lambda. I should recall that the root vectors of the compact operator are linearly independent. A sequence of the subspaces of the Hilbert space is called a basis from the subspaces if an arbitrary element has a unique decomposition. We can learn in detail the properties of the sequences from subspaces in the well-known monograph by Krein, represented here. Throughout the paper, we can consider an operator W with a discrete spectrum. It means that the operator is densely defined and has the inverse, which is compact, denoted by symbol P for the convenience of writing. Also, we use a special notation for the eigenvalues of operator W. In accordance with the definitions, they are characteristic numbers of the operator B. We denote eigenvalues of the operator B. We assume that numerical range of values W belongs to a sector, and it is following contour in correspondence to the sector. I should show it to you. So here we see a contour. Contour close or close-wise direction. Close-wise direction here is chosen. This contour spreads to the infinitely distant point, and here we see this contour. Page 1. Additionally, we make some assumptions with respect to the operator P. P belongs to the Chatin class defined here as n singular numbers of the operator B. Now consider the Riesz integral defined by this formula. Theta q is a contour of the complex plane containing the eigenvalue lambda q only. Only so lambda q inside the area enclosed with the contour theta q. I should remind the following property of the resolvent of the operator W. The Riesz integral is a projector onto the subspace defined above root vectors plus subspace, I remind, along with the subspace M. Consider a formal decomposition. Here we have projectors and a double inner sum can be deleted, but here we should put brackets in the series, and we may say that series is convergent under a suitable arrangement of brackets. M mu is some subsequence of natural numbers. So if this relation holds, then we can say that spaces H mu forms a basis in Hilbert space H, where H mu defined as follows. I should remind that previously we made definitions on the sequence of subspaces. Consider a Lidskii integral corresponding to the eigenvalue lambda q. Here we see a modification of the Riesz integral by involving the multiplier of the exponential type under the integral construction. The main question, it's rather reasonable question that may appear. For what? Certainly for better convergence of the integral on the infinity, or in the neighborhood of the infinitely distant point. But another second question, what about little than exponent function? Maybe another function, not so strong. This question is reasonable also. But following to Abel results, we can do it, and we can say that this kind of Abel convergence. Lidskii tried to evolve exponential function, and I think this is why it's called Abell-Lidskii method, or method of summation. Now we try to connect integral with sum, and then note that this operator, I mean Lidskii integral, acts in H. It maps H to root vectors of subspace, but it's not a projector. It's not a Riesz projector. But when t tends to 0, it it tends to Riesz projector pointwise. So if we have element F, then we have define the convergence of the root vector series in the Abell-Lidskii sense as follows. There exists a subsequence of natural numbers so that the following relation holds. Firstly, we should summarize this series, and after that, we should take a limit when t tends to 0. And in this case, we have the element F. We can compare it with the unit decomposition in the spectral theorem, and we would be right. It is a very generalization of the decision. The Lidskii method of root vector series summation is based upon the following formula. So Lidskii proved this formula, and the principal condition is S must be more than the so-called convergence exponent in terms of the entire function theory. But here we see that you don't obviously. The parameter S is called summation order in the Abell-Lidskii sense. So the simple summation. Lidskii established his famous results in this paper. So the method is very interesting. It's very comprehensive. Prehistory of the problem. Now I would like to state the problem of decreasing of summation order. I want to stress that this problem is a very problem of functional analysis. It's a theoretical problem. It starts from 1962. Lidskii tried to consider to decrease the summation order, not for the general case, but for the case corresponding to the perturbation of the self-adjoint elliptic operator of the second order. More generally, the problem was considered by Katsnelson in his PhD thesis, 1967, for perturbations of the positive self-adjoint operator under the strong subordination condition. The detailed substantiation of the method allowing to decrease the summation order was represented by Agranovich in 1990. Here I represent their papers by Lidskii. The latter, I mean, Agranovich strengthened the sectorial condition and replaced the condition upon the asymptotics of the singular numbers under the following conditions extracted in the operator class, which may be called by conditions of the abstract uniform ellipticity. So Agranovich sectorial condition and strengthened it by range within the domain of the parabolic type. So this condition is rather strong in comparison with sectorial for the reason that the operators satisfying this condition must have the main term, major term, self-adjoint. So this condition is suitable for operators for perturbation of self-adjoint operators by non-self-adjoint operators, generally speaking. Here we see the condition of the uniform ellipticity. If we consider H plus, take H plus equals Sobolev space H01 and H L2 space, functional space. This sign means compact unbidden. And we will have conditions for the uniformly elliptic proof. This condition of the so-called inclusion numerical range of values in the domain of the parabolic type, we can, using simple reasonings, show that imaginary part less or equals real part with some power, and it implies that numerical range is in the parabolic time domain. This condition is very interesting, for it appeals not for singular numbers, but for eigenvalues of the real component with the index p, exponent p. In this way, Agranovich made completely different way to compare his result with Lidskii, but I want to connect a little the results and try to show to you. The main Agranovich result claims that the order of summation can be decreased to the following value. You see, let's analyze condition 3. We are compelled to assume that convergence exponent, I recall, more than 0. Why? You can ask me. I answer. For in another way, which in the contrary way, we should admit that the summation order can be decreased to an arbitrary positive number, but it's the main idea, claimed idea of the Agranovich paper to decrease, to establish the summation order, lower bound of the summation order. And in this way, we should do nothing. And the paper is that. So try to consider the following relation obtained by the author of the report. And using this relation, connection between eigenvalues of the real component and singular numbers, we can establish the following relation. So we more precisely, we can choose a particular class of operators, not general, a particular class of normal operators, for which the condition 3 would be implemented automatically. So having as an assumption the fact that sigma more than 0, choosing concrete operator class that is rather wide, should agree with me if we consider normal operators, we come to the conclusion that this condition holds, you see, for some values, certainly. So it's not a contradiction, it's not, I may say, some kind of disadvantage of the results, but it's a kind of connection between results. We can connect them. And here I should demonstrate using this relation that formally, if we choose Q equals to 1, sectorial case, you see, parabolic case, Q less than 1, if Q tends to 1, the domain enclosed within parabola tends to the domain enclosed to this within the sector. And we come to the Lidskii results. For here we have just a convergence exponent, and here we have S. You see, I can resume the closer to the sector, the less relevance of the formula. But it's all for concrete operator class. So let's proceed our narrative, and now we come to my own results. The main result is based on the following fundamental concepts deserve to be considered separately. First of them, splitting of the eigenvalues. Second one, discharging of the spectrum.
sharper estimate for the canonical product, convergence of the double series, and the reminder, higher values of the shortcomings. So to obtain a result that claims that we can choose as a summation of an arbitrary small number, we should consider properly the concept by Lidskii and others. It is based on the theory of infinite determinants and the entire functions theory, and it is based on estimation of the infinite determinant from the above and from the below estimates. We will consider this question, but now we want to use asymptotics, not singular numbers, but eigenvalues. The main idea, my idea, principle, different from Lidskii and others, to use asymptotics of eigenvalues, not singular. And this is why we make some kind of discharging of the spectrum. We take subsequences of eigenvalues. The matter is, if we take a subsequence, it will have asymptotics more faster than the asymptotics of the main sequence. You see, the main idea is so consider such kind of sequences, and here we have the whole part of this number. Beta is an arbitrary small positive value chosen, and we can consider such a subsequence of natural numbers. Let's rearrange the sequence in the following groups corresponding to the numbers. We can rearrange. We can choose these pairs, and we can count each subsequence by this function, and this would be a counting function for eigenvalues, and this would be a counting function of a subsequence of eigenvalues. So in this way, we split eigenvalues in the groups. So in the domain, we have the following number of eigenvalues of the operator P. And we have the following relation. Certainly, I show it to you for convenience. Maybe I think understand what is it, but let it be so. So denote by n are the counting function of the characteristic numbers, and nk the counting function for the kth group of the characteristic numbers. I should explain that it is the very number of characteristic numbers that is in the circle of the radius r. See, we should choose radius and define number. We have the full lemma. Sorry. Question? No? So we have the following lemma. Assume that P in the trace class, then the following relation holds. So we have the following asymptotic for counting functions. See where beta is an arbitrary small value choose previously. But what should we do with such interesting and fast asymptotics? Firstly, we should make some reasonings in the framework of the functional analysis to apply uh, these asymptotics. And we do it, we did it. The following theorem: assume that B is a compact operator having a set of eigenvalues μg. Then it induces a compact restriction pk on the invariant subspace mk, invariant subspace, obtained as a closure of the root vectors corresponding to an arbitrary subset of the eigenvalues. The operator pk has the eigenvalues only. This is the main fact, the main central point, that K has the eigenvalues only. So it's a kind of, I may say, but not modification, but it relates closer to the theorem established in the monograph by Goldberg-Krein, where we have a decomposition on finite dimensional root subspace and infinite dimensional root subspace. I showed it to you previously, the direct sum of two subspaces, root vector subspace and its parallel complement. So it relates to this theorem, and it is based on this theorem, but some modifications appear. In accordance with the lemmas, we can construct compact operators pk having the set of the eigenvalues defined in the previous lemma. Then pk maps mk into k has eigenvalues m, k, j with the following asymptotic. You see, asymptotic is very strong. For beta is small. So now we can use operator pk and try to reformulate partially Lidskii results for operators pk. For this purpose, we should consider estimate of the Lidskii calls this operator resolvent. It's not rather resolvent, but we may call it also resolvent. So, trying to estimate the norm of the resolvent, we should consider this relation is a classical relation. It appeals to infinite determinant theory, and it is well-known relation. It holds if the operator is in the trace class. Then we will have this. So we should consider, but here everything is spoiled by this project Q1. It bothers us a great deal. It makes obstacles to use asymptotic of eigenvalues, but not for singular numbers. And this is why we should do something with this operator Q1. Q1 is the projector into orthogonal complement of an arbitrary chosen element F. So we choose an arbitrary element of the Hilbert space F, and right now, from that time on, we obtain some kind of project Q1. So we should consider one-dimensional subspace generated by element F. In this case, we have an orthogonal complement of this element, and can consider corresponding project orthogonal. Lidskii tried to diminish this problem in the following way. He proved that following relation holds for singular numbers, and in this way avoided project Q1. But this, in my opinion, rather rough estimate. For what reason? I can answer. For the purpose that we can evaluate eigenvalues by singular numbers by not vice versa. We do nothing knowing asymptotic of eigenvalues. What about singular numbers? So, using this estimate, Lidskii obtained a chain of estimates this way, and final step is to find this exponential function with the following asymptotics. You see, sigma is the index of the Chatin class. So, but we can do something like this, estimating, but not singular numbers, eigenvalues, and try to find beta asymptotic. We do it. We did it. We have lemma 3. This lemma is, the proof is rather complicated. It appeals to infinite-determinant theory. The claim is rather simple, but proof is not. So, using this estimate, we can implement the chain of simple reasonings related to the entire function theory and obtain the desired result in the following. We can obtain this estimation, and here you see S. S is very small. So here we can proceed, and I should recall that the so-called Cartan estimate used if we want to estimate a holomorphic function from below. But here we should deal with the exceptional set of circles. It's not good, but at this step, we are satisfied. So we have the following lemma. It is, I may say, an adopted version of the Cartan estimate theorem represented in the famous monograph by Levin, the functions. So if we have such asymptotics for eigenvalues, it's a counting function for the eigenvalues. Then for arbitrary numbers, such that there exists a circle, so that the following estimate holds. Here, I mentioned nothing on exceptional set circles. You can ask me what, and I can tell you. For here, I have chosen delta a sufficient with sufficient coefficient that satisfies the conditions, and it gives me a simplified form of this theorem. I want to represent it more simple, excluding one of parameters. So what about HR? HR has the following asymptotics. This lemma is the main tool for the proof of the following Lidskii integral convergence. Now we come to the main proposition, theorem 1. Assume that B is a compact operator. B is in the trace class. B is sectorial, belongs to the following sector. Semi-angle less than P divided 4. Then the order of summation in the Abell-Lidskii sense can be decreased to an arbitrary small positive number. See, it's a principal result of the functional analysis. You can decrease an arbitrary small positive. So what about sectorial condition? You can ask me theta less than P divided 4. It's a technical condition. But now I can see how to do it. I should study this matter properly. The idea of the proof is to implement the splitting of the spectrum, having used lemmas 1, 2, then to employ newly created asymptotics of the operators K and applying lemma 4 to estimate the norms. I think to explain the proof, it's not so easy. You can read it in ArcSieve. It is represented there, a complete proof in preprint material. Now I can tell you that the idea is in the following. Here at the left side, we see a sum. We see a sum where up the sum is some number, you see? And the idea to decompose this sum, it's a Lidskii sum, to another sum where we see a projectors corresponding to the operators PK. After that, we prefer to deal with this sum and want to prove the absolute convergence of this series. If we prove it, we obtain the desired result. This series is convergent also. And in this way, we obtain the convergence in the Abell-Lidskii sense, but brackets should be replaced. And so brackets should be replaced. Elements, there is no changing of elements, just replacing of brackets. So I want to demonstrate page 2. You see here we see a sequence of radii, mu sequence of radii. If we consider a term of sum, outer sum, it's a term of outer sum. You see, we have that eigenvalues within the quantum gamma, and this counter gamma, we have expression of this integral in the form of sums, where EQ is greatest. So, but we want to consider improper integral. We want to consider improper integral, and here we consider the counter that origins from not zero but from some value and ends at mu plus 2. So, if we would like to prove that the series at the right hand side is convergent, we can the fact that integral improper integral is convergent at the left side, and in this way show that this series is but here I will show you that previously considered the composition the projectors PK, and summarizing this series, we can use its result in each case corresponding to operator PK. And in this way, the idea to summarize this series. You can ask me, what about equality? Is it so that there exists such a number, natural number, that the terms are equal to both? See? And I can answer, we can. We can use such a sequence are that Lacan appears. You see, Lacan, I try to write it here.
but Laken doesn't contain any eigenvalues, and this Laken makes these sums equal. We don't care about in what number Laken will appear. We don't care about this length. For us, sufficient that Laken appears, but we can do it we can prove it comparing counting functions. And so it's a kind of description of the proof, but let's so high values for the Chatham Lidskii obtained his results for the trace class, and after that he used some kind of trick, this decomposition, and this equality named by form for equality of some kind of equation, and in this way he showed that if we operate a B belongs to the Chatham class with arbitrary index, then EM belongs to the trace class. And in this way, try to bring results, to spread results, high values in the Chatham class. We can do the same, but with some complications. We can consider an arbitrary Chatham class, and then we can use this fact that this equality that you can verify, check it with A equals 1. You can check it this way. The very beginning certainly requires some accurate proof. So, and in this way, we can spread our results to high dimensions, but right now we are interested in the fact that trace class it's decreasing summation. I stopped at the paragraph evolution equations. Lidskii dealt with natural numbers of derivatives, but I tried to involve fractional derivatives, and but technique is the same. Frankly speaking, some modifications appear, and we can consider a Cauchy problem in this way and formulate this theorem. Assume that the conditions of the theorem 1 holds, then there exists a solution of the Cauchy problem in the form. Here, alpha is an arbitrary small positive value. So it's clear that it leads us to such results, but I want to show it to you. Having such a fact that we can decrease the summation order, we certainly have some we are free with dealing with such kind of equations. For here, we shouldn't impose a conditions on the Chatham index of the operator B. So I should stop here. Thank you very much for your attention. Thank you.
Thanks for your talk. Now attendance, now discuss and maybe some question from participants. Do you have question, please?
I have a question.
Okay. Arsen.
Now, what does it mean W in equation 7? What is it?
W, it's the operator defined above with a discrete spectrum. Satisfied
satisfied here, W. Is an operator, W, with a discrete spectrum. The operator is densely defined and has the inverse Riesz compact. You see, B is the inverse here. And the following condition is imposed on the operator W. Sectorial condition belonging to the trace class, and the condition imposed on the semi-angle. So,
Thank you.
so we have a rather wide area of operators for application if we mean the right hand side of, or not right hand side, if we mean operator W. We have a rather wide area of operators for applications.
Thank you.
So, more
Thank you for
question?
the question.
Yes, I have a question.
Taylan Demir.
Dear Professor, thank you for your presentation. My specific field of interest in fractional calculus and their applications, but I want to ask a question about this. Can we apply Atangana-Balanu fractional operator in this here?
Sorry, pronounce one more time. Operator, what operator?
Atangana-Balanu fractional operator.
Frankly speaking, I didn't interest in. I didn't have the interest for this operator, and frankly speaking, I can't answer right now. I should consider this operator. But
Okay.
I can tell you that if this operator is generated by some kind of semigroup, or it
Yes.
is represented by infinitesimal generator of some semigroup, then we can
Okay.
apply these results. It's a more general, vision. It's more general understanding for fractional differential operators. Representation, Alaparena-Shuraliyev written some paper regarding this matter. So you should check it, please. It helps you not applying these results, not only applying these results, it helps you in your future work to deal with this operator in this way. So, but we can verify this question. I should see a construction of this